Okay, in this video I'm going to talk about the Lagrange's mean value theorem. So basically the theorem is stated as follows. So let's say that we have a function f defined on the interval from ab to real numbers, and we assume that the function f is continuous on AB, continuous on the closed interval AB, and it is differentiable on the open interval AB. So we don't need the differentiability at the boundary points A and B. So and then it implies that there exists such point C, interior point C in the interval AB, such that the derivative at this point C is equal to the f of B minus f of A over B minus A. Okay. Yeah. So let's consider the proof, and it's actually not very difficult to prove. So recall that there is a Rolle theorem that looks similar, but it's like the Rolle theorem is a particular case of this theorem. So Rolle theorem. So in the Rolle theorem, we additionally assume that f of A is equal to f of B, and plus these two conditions, that the f is continuous and differentiable. And then from this it follows that there exists some point C such that the derivative is equal to 0. So like we see that like if f of A is equal to f of B, then the numerator is equal to 0, and so the f prime of C, so the derivative at the point C would be 0. So the Rolle's theorem is a particular case of this Lagrange mean value theorem. But on the other hand, it's not too much more general, because like like we can easily reduce the general Lagrange theorem to the Rolle's theorem by choosing a different function f. So they're actually equivalent, despite like the fact that the Rolle's theorem seemed to be more restrictive. This condition adds an additional restriction, but it's actually not a very restrictive restriction, kind of. So Yeah, so essentially we define a new function. So we define a new function g of x as so we define it as f of x minus, then we take this expression, so this this expression which is a constant, right? It doesn't depend on x, so f of b minus f of a over b minus a. So this expression multiplied by x. So that's so we define this new function g of x. So now we check what values it takes on the boundary values a and b. So g of a is equal to f of a minus f of b minus f of a over b minus a multiplied by a, right? And g of b is equal to f of b minus f of b minus f of a over b minus a multiplied by b. And so we need to check that, g of a is it equal to g of b. Well, we just directly check, so we write that f of a minus f of b minus f of a over b minus a multiplied by a is equal with the question mark. We don't know that it's equal, but we want to check if it's equal. F of b minus f of b minus f of a b minus a multiplied by b. So now we move so we move f of a to the right hand side and this to the left hand side. So this we move to the left hand side and this we move to the right hand side. So we get f of b minus f of a over b minus a multiplied by b. So this I took this term minus, I keep this term as is. So f of b minus f of a multiplied by b minus a multiplied by a is equal with the question mark to f of b minus f of a. So f of b I kept as it is and I took the f of a to the right hand side, right? So that's what we get. Now the left hand side can be simplified, so this is the common multiplier. So we get f of b minus f of a over b minus a multiplied by b minus a, and on the right hand side f of b minus f of a. So now we see that b minus a and b minus a cancel each other and we get f of b minus f of a is equal to f of b minus f of a, right? So this is true, so this equality is true. Therefore, because we all the transformations that we did with the equalities were two-sided, like they were equivalent. So therefore, like, we can remove basically the question mark here. And therefore we can remove it everywhere before that, because all the changes to the equalities were equivalent. So we verified indeed that g of a is indeed equal to g of b. So if also like g, the function g is also continuous, continuous and differentiable, but because when we add this term, like, it doesn't violate continuity and differentiability. Well, because this is continuous, and this itself is continuous because it's a linear function. It's trivial to prove that it's continuous and differentiable, and we know that the sum of two continuous function is continuous, and the sum of two differentiable function is differentiable. So g of x is continuous and continuous on the closed interval ab, and differentiable on the open interval ab. Therefore we can apply the Rolle's theorem because we get this additional condition that g of a is equal to g of b. Therefore we can apply the Rolle's theorem and conclude that there exists such intermediate point. So by the Rolle's theorem, there exists such point C in the open interval such that the derivative of g of C is equal to 0. Now, what is the derivative of g? The derivative, so again, g is this function. So from this we can calculate the derivative of g of x. It would be the derivative of x of f minus, so the derivative of x is 1, so minus only this constant. So minus this f of b minus f of a over b minus a. So that's the derivative of g. So we rewrite now this, what we proved. So we get that the derivative, so g, so let's write it here. So this is equal to the derivative of f at c minus this constant f of b minus f of a over b minus a, right? So this is 0, so this whole expression is equal to 0. Therefore the derivative of f at c would be equal to f of b minus f of a over b minus a, and that's exactly what we needed to prove. So we found an intermediate point c such that the derivative at this point is equal to this value, and this is exactly what we needed to prove. Here. Yeah, so this concludes the proof.